Alright, we're going to use our temperature control lab, and we're going to use it like an on and off switch, so 100% or 0%, and we're going to be able to do that in order to simulate a second order system. And we're going to practice fitting a second order system constants graphically. So let's go ahead and look at our code. Similar to what we've seen before, we're going to clear all, close all. We're going to look for a CSV if it exists. If it doesn't exist, well, if it does exist, we're going to read these three columns. If not, we're going to go ahead and do some on and off control. Now what that means is we set our timer, we set our arrays, and if our temperature is under 40, our heater setting is 100. And if our temperature is over 40, our heater setting is 0. Then we implement it and we graph it. So you can go ahead and watch. First of all, it's very cold where I am right now. We're at 15 degrees. The air conditioner is stuck on. So that's fun. And then as we hit 40, you see the heater shut off. We go down, it turns on, we go up, down, down. We have some oscillation. You can notice the frequency is starting to pick up. So what we want to do now is we want to use that image. If I can get everything just right, we're going to use this image right here. Let's move this over. Scroll, and then this, we're going to scroll just a bit, and this process we have here to fit our second order differential equation that we have here. So you notice we have a second derivative of time with respect to tau s squared, or multiplied by tau s squared, plus 2 times this zeta times tau s times temperature 1 over the derivative of temperature with respect to T1, plus the temperature itself. So not the derivative, but itself is equal to Kp times Q1. So let's go ahead. If you remember our FOPDT, it was like just this right here. It was the tau times dt1 dt, and it was minus T1 is how we usually wrote it, plus Kp times Q1. So we're adding a little bit more, trying to reflect this system better. So our first step, and let me just see if I can get everything just right. You notice a couple different characteristics. First we have the delay, which is the time between when our heater turns on and when we actually start to see a difference in temperature. The next is the rise time, the time it takes to get from when it started to that chain, to the set point, I should say. This right here, the difference between the input and the output temperature when the temperature would stabilize, would be our delta T, if you will. And then we have our peak time. We have our decay ratio, which is C over B. C is the you see these different oscillations, and so it's the ratio between the second oscillation and the first oscillation, where it overshot once and overshot again. So we're seeing that magnitude of oscillation decay. So that's where the decay ratio comes from. And our overshoot ratio is this B, how much we overshot versus the change itself. So let's go ahead. Let's look at our process. Let's come over here. Let's make our graph a little bit bigger so we can see the whole process. And let's go from there. So our first comment is, what is the delta T1? Well, delta T1 goes from, and we can go all the way back. We'll call that 16. We'll call it 16. So our delta T1 is going to be, I'll just get the pen out, we'll just do it all together, is going to be 40 minus 16, which is going to be 24. For me. For you, it might be a little bit different. Our delta set point from the start to the finish. Well, now, what's the difference between delta T1 and our delta set point? And that's a good question. Let's go ahead, let's look at our system here. So let's go back. I should have been a little bit more specific with our delta T1. We're going to look at the graph. We're going to look at what the final temperature, like what this actually is about, and it's probably right about right here. It's probably about, I would say, 40, 41. You know, it's what that average temperature is, what it's settling down to. And unfortunately, this is wanting to save as an animation and not a, here we go. let's zoom in. Can we not? Zoomed in on the wrong thing. Zoom in right here. All right, we'll go ahead and just not care about it. Oh, now we're able to. There we go. Let's look what it's about. It looks to me like it's about 40, 41. I would say about 41. So it's that the delta T1 is what the actual change in the temperature ends up being. So delta T1 is actually not 24, but we'll call it 25. Let's go ahead and scroll. And now we're going to use the, first let's set this back to normal so we can see everything. So let's go ahead. This is going to be, wrong tool, it's going to be 25. Delta set point, before it was at 16, then it goes to 40. So that's going to be a 24. So Kp is delta set point over delta T1 over delta set point. I'll need to edit that afterward. So that's going to be, let's see, it's 25 over 24. The actual change in temperature over the set point change in temperature. Now we look at the damping factor, which is, we get that from the overshoot ratio or the decay ratio. And again, there's some typos here. So I will be sure to fix those. I'm making a note of that now. All right. Let's go back. Just look at our ratios here for a second. Let's discuss those. Our overshoot ratio is, again, that B over A, so how it's diminishing. And then the other ratio we could use to determine this zeta is the decay ratio. So so overshoot ratio is B over A, so that the overshoot over the change in set point, where it kind of settles down. So not the change in set point, but the change in final temperature. And the decay ratio is the difference between those two peaks. So which would be easier for us in this system? If our change in set point is right along that 40, well, my thought is I think the decay ratios, actually no, right here. We can figure out what this temperature is right here pretty easily. So let's scroll back out. We're just going to play with the time. Let's go ahead and just plot it again. It's easy enough to plot. We've already saved the CSV. That's it. It doesn't plot it. So we'll go ahead and we will write some code to plot it ourselves. So we're going to plot tm underscore and then t1. You read my mind. And then we're going to say, and we're going to do that with, you know what, let's just not get fancy. Let's just get something done. Then we're going to say hold on. And we're going to say, actually, we're going to call that good. Quick, simple. That's what we're going for. There we go. So our change is just about to 45. We'll give it to them. So our overshoot is going to be change in temperature, which was to 41. We'll go ahead. We'll get out the pen again. Overshoot is equal to our overshoot ratio. So that's, if we think right here, that's our final temperature. So we'll say that's 4. So 4 over, and then this B right here is 41 to 16. So that's going to be 25. So that's what our overshoot ratio is. So our overshoot ratio is 4 over 25. Then we need some relationships that we have from, let's see if we have them here, or we may need to go to the course page to see, or the lesson. It looks like we do need to go to lesson, so we'll just open up our folder, go, that's the assignment, not the lesson, lesson. So we'll see, where do we get these constants, you may wonder. Overdamped is zeta minus 1, critically damped, it's the definition of these different things. Process time, we simulate. Where's the relationships? Did I scroll past them? Here we go, graphically fit. Okay, we need to define these sometimes. So rise time is going to, we have relationships between peak time, rise time, overshoot ratio, decay ratio, and period. And I'll make sure that they're listed here after this. It looks like we, there we go. Knew we had a list, here we do. So overshoot ratio right here is going to be equal to, so we have some overshoot ratio which is equal to some relationship of zeta. If we have zeta, we want to get the overshoot ratio. Vice versa, if we have the overshoot ratio and we want to get zeta, we can go ahead and do these. So let's flip over to our temperature control lab and let's plot that. So graphic fit, so with delta set point here, that's going to be 24. Forgot we already had this down here. Delta T1, we went ahead and said that was delta T1 went to 41 from 16, so it was 25. So overshoot ratio was 44 minus 41. That's close. We were going to say that's 45. And our 41 over 21, instead that was an initial 16. So then our tau p, Kp, let's think this through. Kp we had it before. I'm not sure what, we'll get to Tp in just a second. Kp was from the delta T over delta set point. Our ln os 2, so the log of our overshoot, and then zeta, that's just simplifying this, so is a square root of the log of our overshoot divided by pi squared log of our overshoot. We'll check the function, or log of our overshoot squared. So you see that right there, and we take the square root of that, and that's how we get our zeta. So then let's move on. Our tau s. What's the equation for our tau s? Tau r, tau p, tau s is equal to 1 minus zeta squared over pi times tau p. So these two are related to one another. Tau p is equal to pi tau s divided by 1 minus zeta. But our tau p is our peak time. So let's come over here. I did this before with a different experiment. Let's go ahead and look here, see what our peak time is. Our peak time, my mouse is right there. We scroll down. That's going to be at about 110. But we have to subtract out the dead time. Oh, there we go. That's what I was hoping to get earlier. Oh, now it's doing it too fast. So x is equal to 103, we'll say, right there. 106, okay. We need to subtract out the dead time. We'll do that like we've done before by just looking at, since we started just about instantaneously, we'll look at where this line would cross the x-axis. Right here when at the point of inflection. Running down, I'd say that's maybe about right here. That looks to be right about here. So about 5 seconds. There wasn't much dead time in this system. We know from past experience, though, our dead time is more like 10 to 15 seconds. Oh, we plot all these points. Go ahead and clear them. So our tau p is going to, our peak time is the time from when the heater turns on to when it reaches the peak. So we'll go ahead and say 106 minus 15. Let's go ahead and say 81 is our peak time. That's what we have by this TP. So we'll go ahead and call that 81. And then our tau s is going to be our peak time times the square root 1 minus zeta squared divided by pi. We'll go ahead and look at these equations. Here's our tau s, square root 1 minus zeta squared divided by pi times tau p. What these systems really comes down to is knowing what we have and what we don't have, and then solving for the rest. If it's the rise time, if it's the peak time, whatever we have, we can use those to solve for the unknown variables we have. We could have used period, for example. We could have used other things to solve for this tau s. We could have done it from the period since we have both that and the zeta now. Let's focus on what those values are and then plot our analytic solution. And then you'll see right here this needs a T1. We need to calculate our analytic solution and say that is equal to T1 is what we need to do. So T1 these are backward too, man, all kinds of errors on this one. Who did this? Our T1 prime is equal to this right here. This is our equation with everything in it. Our temperature with respect to time, or deviation temperature I should say, is equal to Kp times delta Tsp times this. Again, this is nice because we're taking these higher order equations and we're regressing an actual system rather than doing as we did before and solving explicitly at every point. So let's go ahead, let's just set this figure up. Do we have time? We do. It's Tm underscore. So we can go through and do the whole system now. Our Kp, T1 is equal to Kp. Let's actually just go ahead. It's going to be 16 plus. That way, instead of being the deviation variable, it's the actual temperature itself. Kp times delta Tsp, which is this right here. So go ahead and just copy it. Times 1 minus the exponent of negative zeta times, that's a zeta, not a zeta, times Tm underscore times time divided by tau s. And that's all going to be multiplied by, we'll do parentheses, cosine of time divided by tau s times sqrt square root of 1 minus zeta squared. And that's outside the cosine. So just looking at cosine right here. So the parentheses start here, 1 open, 2 open, 1 closed, 2 closed. Plus zeta divided by square root 1 minus zeta squared times sine of time, which we do our array that we get a whole bunch of values, divided by tau s times one more square root 1 minus zeta squared. And I believe, did I do 1 minus zeta squared? Oh, divided by pi. I was thinking maybe there's another variable I could toss in there. So hopefully that works. Let's just go ahead and run it. There's probably some typo in there. And that's because anytime we do time, we need the dot times. Because this is a matrix operation, but we want to do it element-wise. So this is a dot divided by, here's another time, dot divided by, and let's see if that works. Let's try this one too. There we go. So, colon operands must be real scalars. Oh, this is because this was copied from earlier where we were plotting it in real time. So instead, we're just going to do plot time and plot Q1. So see how we did compared to our original solution. They did T0 with just taking it from the measured temperature control lab data. So they found constants for all of these commonly used terms. So A was square root 1 minus zeta squared. You see how often that pops up. B was time divided by tau s, time divided by tau s. C was cosine A times B, and you'll notice this is element-wise. And then D is zeta divided by A times sine A times B. And so you have this right here. So you'll notice for our system, we reach it, we're a little bit off in that we need a little bit more oscillation happening, so we underestimated our damping. So let's go ahead and let's just say that our overshoot ratio was a little bit higher than what it was, and that our time to reach this set point time, we need to adjust that as well. So we'll go ahead, let's just change this to 90. And we'll change this overshoot ratio. We want a little bit more oscillation, so we'll say that this is, we'll say that we overshot by 6 instead. Let's go ahead and run the selection, see how well our fit is. It's much better. It's a little bit high this time, a little bit less oscillation, so maybe we involve the periodicity a little bit more. But this is fitting pretty well, so let's go ahead and just play with this a little bit more. Let's go ahead and just say 100. We didn't see much of a dead time in this system. And it could be just because it was so cold that we already see that. So there you see, that's going well. As far as the oscillations, we would go ahead and fit some more with some of these constants. Maybe it's our KP that could use a little bit of tuning. Our delta SP, here we go, that's a problem right there. Delta T1 was not 24, but 21. No, our delta SP was 21. Delta set point was from 16 to 40. That is 24. What we actually saw was more like 16 to 41, 42. So that, let's say that's 26. Not 226. It's going to be crazy. That's where the problem came. We see now we should see some more oscillations. There you do. It's a little bit lulled still. So go ahead. I mean, this is a graphical fit, right? So it's kind of trial and error. Let's say this is now back to 4. So again, we're getting better and better. And that's what we'll do later is we'll actually fit these coefficients in the next lesson. But now you see how we derive these. This process as far as taking the delta 1, taking the TSP, finding the gain, and then finding these factors from those three, as well as any other quantities, is very useful. Having this graph in mind as far as what all of these are is also very useful. And just being able to problem solve. From our lesson, we have these relationships. You should be able to realize what you can solve for that, and then use that to solve for the ones you don't know. Thanks for watching. Please let me know if you have any questions.